Welcome Mechanics of Materials students. In this lecture we're going to go over a graphical method of looking at the normal and shear stresses on a plane that is tilted with respect to the designated X and Y axes for which we're going to apply stresses, normal and shear, maybe to the external surfaces of a body. So we have already covered in a previous lecture the shear stress transformation equation, where we took a slice of material from inside a body with a plane that was tilted with an angle theta with respect to the x-axis, and we put it in static equilibrium, including a normal stress and a shear stress that was appropriate to that tilted plane. And just as a reminder, when we talk about angles of a tilted plane, we're talking about the angle that the surface normal to that plane makes with some designated axis. And in general, it's always going to be the x-axis. So I did allude in that lecture to a graphical method where we would rearrange the stress transformation equations and we'd get an expression that would allow us to graphically represent the shear stress and the normal stress at any angle on a plane at any angle with respect to the x-axis in that body, and so that's what we're going to do now. The graphical representation is known as the Mohr Circle, and that's referring to someone's name. And what we end up doing is, and I'm not going to derive the expression here, you can find that in various textbooks and websites. You can go through the derivation, but just let it be known that you can take the stress transformation equations, the sigma prime xx for the normal stress on our tilted plane, and the tau xy prime or shear stress on our tilted plane, the two expressions for those in terms of your angle and your applied normal and shear stresses in the x and y direction. Eliminate any reference to theta. You can just rearrange algebraically and rearrange terms, and you'll get this expression. So it's just an algebraic manipulation of the stress transformations, but the goal is to eliminate any reference to theta. Well, that'll come in later. So what we end up with in this expression is a first term where we have our normal stress on our tilted plane minus some combination of our applied normal stresses, then we have our n squared. And then we have our shear stress on our tilted plane squared. And then we have a term over here that is nothing other than our applied normal and shear stresses. So presumably we know those. Let me take another step back, be really clear. This is for plane stress. We derived equations with our conditions of equilibrium for a tilted plane using a volume element of a body that was in plane stress. Should have reminded everybody of that when I first started. Now we are still in plane stress, so there's no sigma zz, there's no taus in the z in or on the z face in the z direction. So this particular derivation is for plane stress. Now it could be xy. This particular equation is referencing the xy plane, so we have xy plane stress. It could be xz, could be yz. So as long as it's plane. So if we take a look at this mathematically and we remember our equations for shapes, we'll notice that what we have here is actually the equation for a circle. So we can rewrite this first term as some independent variable x minus a constant a squared. Here we've got y squared, and this is some constant. And it's a constant because it includes terms that all have a defined value. We're assuming that we know or can measure our applied stresses in the normal direction with our xy axes that we're applying to the body. The external dimensions of the body are our fixed axes. Our prime axis, of course, is our tilted plane. So that could change with whatever our angle is. And then the shear is also referenced to our fixed coordinate axes. So if we think about what A and R mean in terms of shape, A is the center of the circle. So we can define the circle center as just simply sigma xx plus sigma yy divided by 2. So the average of our applied normal stresses in the x and y direction. Now this could be, of course, positive or negative, but we're just going to take the average of them, whatever it is. And then our final term is the circle radius squared. So if we took the square root of this whole term, we would have the radius of the circle. Well, if you have a circle center and you have a circle's radius, you can plot it. And that's what we've done down here. So here's our center A, and this represents some body with some combination of normal stresses applied to the x and y faces and some tau xy applied to the x and y faces parallel to them. So we have our center, and we have a radius, and so we can plot a circle. And what the different, if we draw a line from the circle center to the radius, and then we look at the angle that it makes with the x-axis, what we'll find is we're actually defining those angles of orientation of a plane that we could have with respect to the x-axis, you know, out on the body. Except the important thing to remember is when we plot our circle, given what we're plotting up here, remember x is the normal stress on our tilted plane and y is the shear stress on our tilted plane. So we're not plotting against x and y dimensions, we're plotting shear versus normal stress. That's what our circle is actually plotting. So this tau here is really our tau xy prime given xy plane stress, and this is sigma xx prime at wherever. So it's any shear or normal stress. So if we think about things like and I'm going to remove this now just because we're going to end up getting a busy diagram here. So think basically, this takes a little bit of leap of imagination. I'm going to go back and walk through the steps of how we got this shear and normal circle. We take our stress transformation equations that we already derived that express shear and normal stress on any plane tilted at any angle with respect to the fixed x-axis. We load the body up with a certain applied normal and shear stress. We rearrange those equations and we get this. We say, aha, that looks like the equation of a circle. And it would be the equation of a circle in xy coordinates if x happened to be normal stress and y happened to be shear stress. And conveniently for us, the circle center can be defined as the average of the applied normal stresses in two directions, and the circle radius can be expressed in terms of the applied normal stresses in two directions and the applied shear stress, if I happen to have one. Cool. It falls out of the math, literally. It's no mystery. It just is a convenient mathematical rearrangement. So let's just get used to thinking of a circle that's going to have a center somewhere on our sigma, our normal stress axis, and it's going to have a radius that relates to the applied shear and normal stresses on our body that we're loading up, to which we're applying stress. Now let's look at the angles that a line between the circle center and somewhere on its rim would make, because this is where we link back to those angles of orientation somewhere in our body. And let's start by looking at a place down here on the sigma axis where tau is 0. 0 shear. There's some special orientations in a body in which shear is 0. Those are the principal directions where we have nothing but normal stress, and those normal stresses tend to be maximized or minimized for that plane stress case, at least within that xy plane. We'll look at whether or not that's true if we consider 3D later. So if we look at this point right here, whatever angle in the body that happens to correspond to, what we're looking at is our first principal stress here, sigma 1. And likewise over here, this is our second principal stress, or our normal stress minimum, and that's sigma 2. And that we just read that off the x-axis. So we can actually determine those right now. We can determine the magnitudes and signs of our principal normal stresses the minute we plot our Mohr circle. So we would take the circle center, the sigma xx plus sigma yy over 2, and then add our expression for r, and we would have our first principal stress, and likewise subtract r from A, and we'd have our second principal stress. We can get our shear max by just happening to notice that the circle radius, when it's pointed straight up, is our maximum shear. So we can get the magnitudes and signs of our principal normal stresses and our max shear just from the Mohr circle all by itself. What we don't know is what angles those correspond to. So I have to do a little more mathematical thought experiment to correlate the angles in the Mohr circle. Like you can see here, here's an angle alpha, here's an angle beta between these two center to edge lines. How does that correspond to that angle theta in our loaded body that is representing the surface normal of some plane of interest to the x-axis that we can measure on the outside of our part? Well, let's just take a couple of angles, and then let's think about how they would relate to the directions of zero shear and our directions of loading. So we're going to define 2 points on our Mohr circle, and those represent valid combinations of shear and normal stress that you're going to see somewhere in that body. If it's not on the Mohr circle, it's not a shear normal combo that body experiences at any angle. So these are like all the possible combos of all the possible planes at every orientation in the body, at least in the xy plane, sorry, in the xy plane. So we'll take point X, and it has a loading. We'll just assume that this happens to be our applied loads, our applied stresses. So here's what we applied. We applied some sigma xx and some tau, and we obviously can plot tau as positive or negative and get the same a corresponding point down here. But right now we're kind of leaving it open whether tau is positive or negative. But this is the applied condition here. So there's no primes. Okay? So we know that. We can plot that. In fact, we can go over our applied stress in the x direction, and we can go up or down whatever our applied shear is and get a point here or here on the Mohr circle. Okay, now we can relate our applied stress to our principal normals. So we can basically say, okay, I can evaluate alpha as the tangent of our tau divided by sigma xx, take the inverse tangent, and I'll have some relationship of what angle my first principal normal is to my applied load. If I want to define some other plane, some plane beta, some plane at some other angle to my applied stress. So this angle alpha is the direction in which it's the x direction effectively. If I say, okay, there's some other angle that I care about, we'll call it beta. It would represent theta in our original stress transformation discussion. So we got another point out here. It's not the direction that we loaded the body up in. So it corresponds to some other angle. So beta is like, we can say it's like theta in our original discussion. Kind of. It's related to, proportional to, we'll say related to, function of, we'll call it a function of theta from our stress transformation derivation. Okay, so we can define a normal and a shear stress for that point too, and that we're going to see that somewhere in the body. Okay, so let's go ahead and define x prime and x and the angles between them in terms of one another. So I'm going to erase and give a little bit of room. And this takes a few goes, and it will take a few examples. The Mohr circle is a very powerful graphical tool, but it definitely requires a few leaps of faith mathematically to relate what's going on at what angle in the body to what I'm seeing on the circle. And it honestly does take a little bit of practice. But it's well worth it, because when you get used to it, you can intuitively envision what's going on and see conditions of serious interest, like immediately see, what's my maximum tensile stress? I mean, as soon as you plot that Mohr circle, you can immediately see, oh my goodness, I may have, my loading, my external applied stress may be up here, but if I have a large radius to my Mohr circle, say because I applied a lot of shear stress or whatever, I may have some angle in that body somewhere that's experiencing a lot more tensile stress than I applied in the x direction anyway. So that would be something that would be really valuable to know, and all you have to do is plot the circle to see that. Okay, but let's continue with our alpha and beta discussion here. So let's start by writing the normal stress in the x prime direction. So this is our sigma xx prime, for which we derived the stress transformation equation earlier. So in terms of the Mohr circle, the location of that sigma xx would correspond to where that line hits the sigma axis. And we could plot that by going, well, that's A, which is this, plus the cosine of alpha plus beta times r. So just do some right angle trig and some plotting. And there was an error in the notes, so that's been crossed out. It is A plus r cosine of the combo angle. We can use a trig identity and rewrite this as a difference and products, which will make things easier for us later on. And now we're going to take a step back and go, okay, alpha and beta look great on the Mohr circle, but what I really want to know is that angle theta that tells me, okay, how far am I tilted, my plane of interest tilted from something I know, my reference axis, my fixed x-axis. Okay, so to do that, we just, again, do some more mathematical rearranging. So first, we're going to write an expression for, we're going to go back to, okay, let's not tilt the plane. Let's just write an expression for the normal stress on some plane that's tilted and some plane that's not tilted if we don't have any tilt. So we're going to write an expression based on the Mohr circle location of just where's the x-axis pointing. Okay, so that means beta 0. So we're just going to write an expression for this. Okay, so we can say, in this case, sigma xx prime is sigma xx because x prime is x in this case. We're just not tilting that plane at all. Okay, so that's going to be equal to a plus r cosine alpha, because remember, we're going back to this expression, except beta 0, so we're just left with cosine alpha. And then we can rewrite that a little bit by saying, okay, well, what's alpha? Well, alpha is this expression. We'll drop in what we know about alpha in terms of our applied stresses. And then we can basically take sigma xx over 2 and move it over here, and we got sigma xx over 2, do a little bit of rearranging. And now we have r cosine alpha in terms of applied stresses. And of course, r contains all of our applied stresses. Now we're going to do some substitution. More mathematical wrangling. It's worth it in the end. We substitute this expression into our trig identity optimized sigma xx prime expression. So basically, r cosine alpha is going to be going right up there. So we have an r cosine alpha cosine beta. So we're going to take this expression here for r cosine alpha, and we're going to plop it up there into our trig identity altered expression for normal stress on the tilted plane. So here we go. Now we've substituted. So we've written A out in terms of its definition. Here's our r cosine alpha. We're still multiplying it by cosine beta. And now we've got our r sine alpha sine beta term left. Okay. We've still got some alphas and betas in here that we don't want because that doesn't mean anything when we're just looking at our part and thinking about a tilted plane versus our reference axis that we know. So we're going to arbitrarily define beta as 2 alpha here, and we can relate that a little bit if we go back to our stress transformation equation, remembering that we end up with those double angle formulas where we end up having a 2 theta. But at this point we're just going to do it as a substitution. So let's substitute 2 theta in everywhere we see a beta. And in that case, our R sine alpha is going to correspond to tau. It's going to correspond to our shear stress. How do we know that? We're comparing back to expressions in our original stress transformation. So this is a second substitution that we make. So I'm not writing it out here, but that's why we could make this statement here. Okay, so I'm drawing some little lines to to show what terms go where. So in step 3, we take this expression with our R sine alpha substituted for negative tau. We're going to use negative tau, not positive. This facilitates signs. And beta equaling 2 theta, so we do those 2 substitutions. And now we come down and we end up getting this expression for tau xx prime. So the normal stress on some tilted plane, tilted at some angle theta, not 2 theta theta, to our reference x-axis. So we get what's our A, our Mohr circle center, and then we get this term, again, just our applied normal stresses times cosine 2 theta plus our applied shear sine 2 theta. So this is a Mohr circle friendly version of the stress transformations. All we did was some mathematical wrangling, basically. And now we have, we've kind of gone backwards. When we derived the Mohr circle expression, we said, hey, we don't want any terms that have a theta. We want to get rid of those in order to show hey, this looks like a circle with a center and a radius defined in terms of something I know. Now we've backtracked. All of this mathematical wrangling has been backtracking in the direction of saying, well, I want to reintroduce theta because it links me to something on my real part, but I want it in terms of something that's going to make sense on my Mohr circle. So that's what this term does. So if we want to know the normal stress on any tilted plane, tilted at an angle theta, we can use this expression, and it's going to make a lot of sense when we go to plot things on our Mohr circle. So let's use an example here really quick to show how that works. Okay, so we've got a body here, and we've defined the x and y axes like this. And we know what the applied stresses are. We have 10 megapascals tensile, positive 10 megapascals, sigma xx, negative 2 megapascals, sigma yy, and we have negative 3 megapascals, tau xy. So it's on the x face and going in the negative y direction, so we have negative shear. So here's our applied stresses. We can use our definitions of A and R from our Mohr circle, and here's A and R. So we do 10 megapascals plus negative 2 megapascals divided by 2 to get our circle center, and then we use this expression to get our Mohr circle radius. So immediately, just from knowing our applied loading, we know the circle center and radius, so we can plot that. So we end up with a circle center at 4, and we have a circle radius of 6.71. So our first principal stress is about 10.7, and our second is compressive, so it's negative 2.7. So this is A minus R, and this is A plus R. So somebody wants to know something about what's going on at negative, on a plane that's oriented at negative 25 degrees. Okay, so now we got to think of, well, where was 0 degrees on this Mohr circle? So there's the trick. When you use the stress transformations directly, you just plug in 2 times negative 25. Here we got to figure out where 0 is. So we know the x face would correspond with theta equals 0. And we know, because we know what's applied there, we know that the normal stress on the x face is what we applied, 10 megapascals. And the shear stress on the x face is what we applied to the x face, it's negative 3. So we got a point. We got a point on the Mohr circle right here. This is the x direction. It's the alpha, it's the angle that corresponds to a normal stress of 10 and a shear stress, a shear stress of negative 3, except we're plotting opposite with tau in this case. And that's another point that I'm going to make that came out of this derivation. We're going to relate alpha and tau, or theta and tau. We're going to flip tau for this convention. So again, it's another convention to remember, but so that's why 0 looks like it's a a positive rotation on the Mohr circle from our principal direction. We just remember to plot it that way. We'll get easier with a few more examples. So here's our applied load in the x direction, and so we know that our angle alpha going clockwise will be our principal stress direction. So whatever angle alpha ends up being, if you go clockwise from the x-axis, that's where you're going to find our max stress. Okay, go step by step. So first let's figure out what's going on at negative 25. So we use our conventions of 2 theta, and this is what we're doing, invoking this expression basically. So everything is going to be in terms of 2 theta, just like it was in the stress transformations. So we're going to go 2 theta of equaling, or theta is 25, sorry, I'm getting a little tongue-tied here. We're going to go from our x-axis, we're going to go 2 theta in the same direction that we were concerned with on our body. So we wanted to go 25 degrees clockwise. On the Mohr circle, we're going to go 50 degrees, just like we would if we were plugging into a stress transformation. So we're going to have 50 degrees is 2 theta, and that's the difference between our x-axis and our angle orientation of interest. So if we knew what alpha was, we would know what 2 theta was with reference to our sigma axis, and then we could get we could solve for the coordinates of this point, which are the normal and shear stress on the plane of interest. Well, we can get alpha just by taking the inverse tangent of 10 and 3. We've gone 3 up and 10 over from the center. So basically the coordinates of that point minus our 4, so we've got 3, and then we have 10 minus 4. Oop. So here's our tangent alpha. So alpha turns out to be about 26.56, and we know that 2 theta is 50 degrees, so 50 degrees minus 26.56 gives us beta, and that's this part. That's our beta. Once we have beta, we can calculate the position of this point. So it'll be the normal stress coordinate of this point will just be your circle center, 4, plus cosine of beta times r. So sigma xx prime, this is our plane at negative 25 degrees, circle center, r times cosine beta, we've added them together, and then our negative tau xy is going to be sine of negative beta, so we're going to go down, and so we end up getting a 10.2 normal stress and a negative 2.16 shear stress. So there's our normal and shear, that's our sigma xx prime and our tau xy prime for our tilted plane, tilted where its planar normal is tilted at 25 degrees. So key points. Step 1, once you know your applied stresses, plot your Mohr circle. Get your center, get your radius, plot the circle, kind of see where you are. You know, is it all compressive? Is it all tensile? Then go ahead and go ahead and try to find where your x and y axes. We could also take a look at this and go, well, if my x-axis is here, my y-axis in my real part is at 90 degrees from my x-axis. On the Mohr circle, it's 180 degrees. So your y-axis is over here. And that is one of the key points that came out of this derivation, is the relationship to theta, the tilt of any planar normal with respect to our reference axis in our real part is going to transform into a 2 theta in the Mohr circle. So our coordinate axes are 180 degrees apart in the Mohr circle. And this is getting really, really busy, and I apologize. So plot your Mohr circle with A and R. Find your x-axis or your y-axis, one of your reference directions where you know the loading, and then walk along the Mohr circle clockwise or counterclockwise to an angle that gives you your angle that you're interested in. And remember that the theta on the body, it becomes a 2 theta clockwise or counterclockwise on the Mohr circle. Again, coming out of this work. So really there's almost a checklist of rules with Mohr circles that allow you to graphically use your stress transformations. Your center, your radius, the fact that angles in the body correspond to 2 theta on the Mohr circle, and just the simple graphical realization that if you're on the x-axis, you have no shear, and your radius of your circle is always going to correspond to your maximum shear at whatever angle that is. Okay. Last but not least, what we got off of our Mohr circle is probably right up front was the most important thing. We can write our principal normals that we got right at the beginning. So I am going to quit for this lecture here. This is kind of long and tongue-tied, but I'll just go over again. Mohr circle is the same as our stress transformations in that we don't introduce any new concepts. It's just a mathematical rearrangement of the stress transformation equations. We start, rearrange equations, get rid of thetas. Notice we have a circle. We've defined the circle, center, and radius in terms only of our applied stresses, which presumably we would know. When we plot the circle and we start looking at angles in the circle, we can find that angles in the circle with reference to our sigma and tau axes correspond to double what the angle would have been in the part, and that we can use trig to find literally what our x-axis was with respect to our principal normals, which are where the circle touches the sigma axis, the x-axis, the sigma axis on our Mohr circle. And from that we just basically literally use trig and right angles in the circle to determine the shear and normal stress at any angle with respect to the principal axes or to our applied stress axes. So that is it for this lecture. We'll have some more examples on this, practice using the Mohr circle a little bit. We will not return to those derivations. We'll just continue to use the rules of the Mohr circle and get used to moving to different angles clockwise and counterclockwise through the part.